Block 1. The Unseen Anomaly. Hello explorers, and welcome back to the channel where we journey to the very edge of human knowledge. Today, we delve into one of the most astonishing geological mysteries of our time, a story that feels ripped from the pages of a Jules Verne novel, yet is unfolding right now in the quiet, data-filled labs of our world's top seismologists. Imagine a part of our planet so hidden, so profoundly unexpected, that it defies everything we thought we knew about the very ground beneath our feet. We're not talking about a lost continent or a hidden cave system. We are going deeper, much deeper, into the Earth's searing high-pressure mantle. We're talking about an earthquake shadow that shouldn't exist, a ghostly silence in our data where there should be a roar of seismic energy. And at the heart of this enigma is the incredible journey of one pioneering woman who dared to follow its faint, perplexing whisper. Her relentless pursuit led her to uncover what some are now calling a brand new, uncharted world locked away miles below us. So, prepare to have your understanding of our planet shaken to its very core. To truly grasp the magnitude of this discovery, we first need to understand how we see into the Earth. We can't just drill a hole to the center. The pressure and temperature would obliterate any instrument we have. Instead, we use the planet's own heartbeat, earthquakes. Every time the Earth quakes, it sends out shock waves, or seismic waves, that travel through its interior. Think of it like a planetary-scale ultrasound. We have sensors called seismographs all over the globe that listen to these waves. The two main types we listen for are P waves, or primary waves, which are compression waves that travel fast, and S waves, or secondary waves, which are shear waves that move more slowly and cannot travel through liquid. By timing how long it takes for these P waves and S waves to arrive at different stations, we can build a map of the Earth's interior. This is how, in the early 20th century, we discovered the Earth's core. Scientists noticed that on the opposite side of the planet from an earthquake, there was a shadow zone where S waves disappeared entirely. This was the eureka moment. It proved the Earth's outer core was a massive sphere of liquid metal, as S waves simply couldn't pass through it. This established concept of an earthquake shadow became a fundamental part of geology. It was predictable, understandable, and a testament to our ability to decode the planet's secrets. But what happens when a shadow appears where none is expected? What happens when seismic data starts showing a new, unexplained anomaly? A region that seems to swallow or distort waves in a way that doesn't fit any existing model of our planet's structure. For years, these strange readings were dismissed as noise, as data artifacts, or as localized quirks. They were the faint, discordant notes in a global symphony that most were content to ignore. But not everyone. Our story's protagonist, a brilliant and tenacious seismologist, saw a pattern in the noise. She noticed that earthquakes from specific regions, when measured in other specific regions, consistently produced this bizarre attenuated signal. It was as if something vast and previously invisible was lurking deep within the mantle, casting its own faint shadow. The scientific community is, by its nature, skeptical. Revolutionary ideas are met with rigorous, often harsh scrutiny. The idea of a massive unknown structure inside the mantle was extraordinary, and it required extraordinary evidence. For years, she faced this skepticism, meticulously collecting data from thousands of earthquakes. She wasn't just looking at the simple arrival times, she was analyzing the very shape of the waves, their frequency, their amplitude. It was like trying to discern the shape of an object in a dark room by only studying the echoes bouncing off it. Was it just a pocket of unusually hot rock, a collection of different minerals, or was it something else entirely? Her journey was a testament to scientific grit, a refusal to accept an incomplete picture. She was a detective hunting a ghost in the machine of our own planet, following a trail of faint whispers that would ultimately lead to a roar, a discovery so profound it would challenge the very textbook definition of Earth. She was about to find a hidden world. Block 2. Unveiling the subterranean frontier. The transition from a tantalizing anomaly to a concrete discovery was a journey of immense technological and intellectual effort. It wasn't enough to simply point at a strange shadow in the data. Our protagonist had to prove what was casting it. This is where the power of modern science truly comes into play. The key was a technique called seismic tomography. If you've ever had a CT scan, you'll understand the basic principle. A series of X-rays are taken from different angles to build a 3D image of the inside of your body. Seismic tomography does the same for the planet, but instead of X-rays, it uses the thousands of seismic waves from earthquakes that crisscross the Earth's interior every year. By combining data from a global network of seismographs, scientists can create breathtakingly detailed 3D maps of the mantle, revealing areas where waves travel faster or slower. But her focus was different. She was looking for something that didn't just slow down waves, but fundamentally change them. Using supercomputers, her team developed incredibly sophisticated computational modeling programs. Think of this as creating a digital twin of the Earth. They could input all known geological data and then simulate an earthquake, watching how the virtual waves propagated. They could then tweak the model, adding a lens of dense material here, a pocket of partial melt there, and run the simulation again and again, thousands of times. They were trying to build a model of the Earth's interior that could perfectly replicate the strange, shadowy data they were observing in the real world. After years of painstaking work, they found it. The only model that fit the data was one that included a colossal, previously unknown structure deep within the mantle. It wasn't a simple blob of hot or cold rock. The data suggested it was a structure with distinct boundaries, potentially a different chemical composition and crystalline structure from the surrounding mantle. It was, for all intents and purposes, a geological continent buried thousands of kilometers beneath our feet. The implications of this hidden realm are truly staggering, shedding shockwaves through multiple scientific disciplines. First, it completely reshapes our theories on planetary formation. Where did this structure come from? One leading hypothesis is that it could be a remnant of an ancient protoplanet, perhaps Theia, the Mars-sized body believed to have collided with early Earth to form the Moon. While most of Theia was absorbed or ejected, perhaps a massive chunk of its dense iron-rich mantle plunged deep into our own, surviving for billions of years as a distinct entity. If true, we have a piece of another world buried inside our own, a pristine sample of the building blocks of our solar system. Second, it alters our understanding of the Earth's engine, heat transfer. The mantle's slow churning convection currents drive plate tectonics, fuel volcanoes, and generate our protective magnetic field. A structure of this size and potential density would drastically influence these currents. Does it act as an anchor, pinning mantle plumes in place for eons? Or does it act as a blanket, trapping heat from the core and causing supervolcanic hotspots on the surface above? Answering these questions is critical to understanding the long-term evolution of our planet's surface. But perhaps the most mind-bending implication is the potential for life. This sounds like science fiction, but consider this. On the surface, we have discovered life in the most extreme environments imaginable, from volcanic vents to subglacial lakes, often thriving on chemical energy rather than sunlight. These are called extremophiles. Could this newly discovered deep Earth structure host its own unique, isolated ecosystems? The immense pressure and unique chemistry could, theoretically, provide the necessary ingredients for chemosynthesis-based life, entirely separate from our own biosphere. It's a tantalizing, almost unbelievable thought that our planet might not host one cradle of life, but two. This discovery has thrown open the doors to a new subterranean frontier. It proves that after centuries of study, our own planet still holds profound secrets, and that there are entire worlds waiting to be discovered, not in the distant stars, but right here beneath our feet. The age of exploration is far from over. In fact, it may have just begun. What do you think is truly hiding in this subterranean world? The remnants of an ancient planet, or something even more mysterious? Let us know in the comments. Subscribe for mind-blowing discoveries and see you on the next journey.